Section 5.6, the fundamental theorem of calculus. All right, don't get scared about that. The fundamental theorem of calculus, pretty big. But anyway, let's look at it. If f is continuous on AB, and capital F is any antiderivative of lowercase f on AB, then we have this statement right here. Well, that's it. That's the fundamental theorem of calculus. Well, that's part one of it anyway. Okay, what does this mean now? This means, let's suppose I want to integrate a function with limits of integration like this. What this fundamental theorem of calculus tells me I could do is I could do this by hand instead of having to draw a picture and come up with a formula for geometry and so forth. Now, how does it tell you to do this? It says, take an antiderivative, which is f. So find an antiderivative of this function, lowercase f, and evaluate that antiderivative at the upper limit of integration and subtract that antiderivative evaluated at the lower limit of integration. All right, so let's do an example. Our first example says to evaluate. And part A, we have evaluate the integral from 4 to 5 of x squared. All right, so we're going to integrate this. So what does the fundamental theorem of calculus part 1 tell us to do? It tells us to find an antiderivative first of all. Antiderivative of x squared, what is that? That's x cubed over 3. So that's my uppercase f, all right? Now what we do is we write a bar like this and we put our limits of integration from 4 to 5 on that bar, okay? And then we take the antiderivative, evaluate at the upper limit of integration. So take this antiderivative, evaluate it at 5. So I'll have 5 cubed over 3, and subtract from it the antiderivative evaluated at the lower limit of integration. So 4 cubed over 3. And keep going down, I'm just out of room, okay? So what do I get? 125 over 3 minus, what's 4 cubed? 4 times 4 is 16 times 4 is 64, right? Over 3. And do the subtraction. What's 125 minus 64? What would that be? 61 over 3? And that's it. That's how the fundamental theorem of calculus part 1 works. All right. Some of y'all are thinking right here probably, why did I not put the plus c right here? Why did I not put that arbitrary constant? Let me show you why. I'm glad you asked. Let me show you why. All right, so if I would have taken this, the integral from 4 to 5 of x squared dx, and I would have taken an antiderivative as x cubed over 3 plus c, and then put my bar again, put from 4 to 5 here, what would I get? What does that fundamental theorem of calculus part 1 tell us to do? It tells us to evaluate this at 5. So we have 5 cubed over 3 plus c minus evaluate this thing at 4. 4 cubed over 3 plus c. So that gives me 125 over 3 plus c minus, if we distribute as negative, we get a minus what? 64 over 3. And then what? Minus c, right? So what's going to happen here with my plus c and my minus c? They're going to zero out anyway, right? And that's what's going to happen whenever we have these limits of integration like this and we use our fundamental theorem of calculus to evaluate these integrals. The c is just going to zero out each time, so I don't even write it. I just save myself some time there. Part B. Part B. We have the integral from, let me find where it's at. Well, I guess I don't have a part B on that one. So instead of calling it A, we're just going to call that example. All right, now I have my next example. And it tells me to evaluate this one. I do have a part A. It has the integral from 4, well, it's the same thing, from 4 to 5. Oh, my notes are messed up here. Okay, let's try this then. Let's go ahead and recall this A. And then we'll call this over here B. What this is going to make a wonderful video here. All this erasing and everything. All right, so let's say from 2 to 4, 2x cubed dx like this, okay? Now, what we learned in the last section was, what can we do with this 2 if it's being multiplied by the integrand? I can pull it to the outside of the integral side and write 2 times the integral from 2 to 4 of x cubed dx. Well, that's 2 times, let's take this integral. Let's take an antiderivative of x cubed. What is that? X to the 4th over 4? And we want to put the bar, we want to put from 2 to 4 as my limits of integration, okay? All right, so this is 2 times, let's evaluate this antiderivative at 4. So 4 to the 4th over 4. And we're going to subtract from it this antiderivative evaluated at 2. So 2 to the 4th over 4. All right, so that's 2 times, well, let's make the math easy. Isn't this 4 to the 1st like that? Okay, so what could I do? I could call that 4 to the 4th over 4 to the 1st is 4 what? Cubed. How about this part? 2 to the 4th. Isn't that 2 times 2 times 2 times 2? And what this and this divide out? So what do I have? I have 2 out front, and then I have 4 cubed, which is what? 64, minus what? 2 times 2 is 4. So what does that give me? 2 times 60, or what? 120. That's my antiderivative there, okay? Or actually, it's my integral from 2 to 4. Or I can look at this as the area under this curve right here between 2 and 4 is 120. All right, let's go on to the next part, C. C is in cat. C is in cat. We're going to have the integral from -2 to 1 of x squared minus 6x plus 12 and dx at the end. In the last section, we learned that if we're integrating like a polynomial like this, in other words, functions being added, subtracted, we could break it up into the integral of each part, right? All right, so what I'm going to do here, though, instead of writing, technically what I need to do, don't write this, but technically what I need to do is this. Okay? But just to save time, I'm not going to do that, okay? Most people don't break it down that way. At least not, they don't show that step. What most people do is take an antiderivative of this, take an antiderivative of this, take an antiderivative of that, okay? What's an antiderivative of x squared? X cubed over 3, right? Minus 6 times, let's take the antiderivative of this part. What is that, x squared over 2? Plus, how about an antiderivative here? 12x, right? And we're going to run this from what? -2 to 1. From -2 to 1 like that. All right, let me clean this up a little bit. I can say this is 1/3 x cubed minus 3x squared plus 12x, and let me run that from -2 to 1. So now, what do I do with this antiderivative? I evaluate it at 1, so I plug in 1 here, and I subtract from it this antiderivative evaluated at -2. So let's do so. So let's sub in 1. So we have 1/3 times 1 cubed minus 3 times 1 squared plus 12 times 1 minus this antiderivative evaluated at -2. Let's see. So I have 1/3 times -2 cubed minus 3 times -2 squared plus 12 times -2. What does that give me? 1/3 minus 3 plus 12 here, right? How about over here? What's negative 2 cubed? Isn't that negative 8? Negative 8 times 1/3 is negative 8/3. Times this negative gives me what? Plus 8/3, right? All right, negative 2 squared is 4. 4 times negative 3 is negative 12. Negative 12 times negative 1 is plus 12. And this gives me negative 24 times negative 1 is what? Positive 24. Now just calculate this stuff, okay? Let's see. What's 12 and 12? 24 plus 24 be 48. 48 minus 3 is what? Yes, you guessed it, 45. What's 1/3 plus 8/3? That's 9/3, right? The 9/3 is what? 3. What's 45 plus 3? 48. 48. All right, let's look at D. D is in dog. D is in dog. So if I look at part D, I have the integral from 4 to 9 of 2x square root of x dx. Oh, got a nasty square root. Is that going to bug us? Absolutely not. All right. First thing I'm going to do is I'm going to pull this 2 to the outside of my integration symbol and write this as the integral from 4 to 9 like that, okay? Then this is x, so I could say x to the first. But what is this? This is x to the 1/2 dx. So we drop down our 2, drop down our integration symbol with the limits. Now if I multiply these, that's 1 plus 1/2 for what? 3/2 dx. Now let's take an antiderivative. 2 drops down. If I take an antiderivative here, what is that? That's x to the 5/2 over 5/2. I can say times the reciprocal, 2/5 from 4 to 9. Okay, now it's your choice right here. You can actually factor this 2/5 out if you wanted to, or you can leave it there. It doesn't really matter. What do you prefer, you toilet paper? Going over the top like that, or going over the bottom like that when you put it on the roll? It's personal preference, right? All right, so we have 2/5 times, let's go ahead and write a bracket there. 2/5 times 9 to the 5/2 times 9 to the 5/2 minus 2/5 times 4 to the 5/2. Let's see. So I'm going to have a 2 out front. Now, we have 2/5 there. Actually, I'll tell you what, let's go ahead and factor it out now. I don't know why. But let's go ahead and factor this 2/5 out from here and here, okay? Bring it with the 2. So that'll give me 4/5. Then on the inside, I'm going to have 9 to the 5/2. Or, couldn't I write that as the square root of 9? The square root of 9 to the 5th like that. Minus, I already factored out the 2/5. Instead of 4 to the 5/2, I could write the square root of 4. What? To the 5th? Like that. Well, let's just calculate. So we have 4/5 times, what's the square root of 9? Square root of 9 is 3, so 3 to the 5th, minus square root of 4 is 2 to the 5th. All right, so that's 4/5. What's 3 to the 5th? 3 to the 5th. 3 times 3 is 9, times 3 is 27, times 3 is 81. What's 81 times 3? 243. Minus, how about 2 to the 5th? Yes, it's okay to count on your fingers, okay? Whenever you do it exponents, because you're counting and trying to multiply at the same time, okay? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? By the way, you made it to calculus now. Count on your fingers. Who cares? All right, so that's 4/5. What does this give you? 200 what? 11 Oh, so what does that give me whenever I multiply? 844 over 5. 844 over 5. Part E is an elephant. Part B is an elephant. Let's see. I'm going to have, let's evaluate the integral from natural log of 11 to 4 of 11 e to the x. All right, first thing I like to do, pull that constant factor out. Write this as natural log of 11 to 4 of e to the x dx. So 11 comes down. What's an antiderivative of e to the x? That's the easiest one to take, right? It's itself. E to the x. What do I need to do? I need to run it from natural log of 11 to 4, right? So what does that give me? 11 times e to the 4th minus e to the natural log of 11. So that's 11 times e to the 4th minus, what happens here? What if this base e matches that base up here? Then I can drop everything except the 11, right? And if I distribute the 11, I get 11 e to the 4th minus 121. I guess you could leave the answer above it. It doesn't matter. I mean, if you like it in factor form, that's fine. All right, let's look at our next example. Again, they want us to evaluate some integrals, okay? They want us to evaluate some integrals here. Let's see what we have. For part A, we have the integral of 0 to pi over 3 of the secant of theta squared d theta. Oh, good old trig functions, right? Well, how are we going to do that? Well, let's take an antiderivative of this. What's the antiderivative of secant squared? Well, what you do is you think, what do I take the derivative of to give me secant squared? Yeah, I know some of y'all are screaming right now at your YouTube screen saying, tangent. All right, that is correct. So that's the tangent of theta. We need to run it from 0 to pi over 3, right? So now what do? I evaluate the tangent of pi over 3 and subtract the tangent evaluated at 0. So tangent of pi over 3 minus the tangent at 0. Unit circle time, right? Didn't I tell you how to memorize the unit circle at the beginning of the semester? I didn't tell you to memorize it for S and G's. I told you to memorize it because you're going to have to use it over and over and over again, right? So which point are you at here if you're at an angle of pi over 3? Well, you're at the point, what? 1/2 comma square root of 3 over 2, where 1/2 is the cosine and square root of 3 over 2 is sine. And isn't the tangent the sine over the cosine? So the tangent of pi over 3 is the sine value over the cosine value, or the square root of 3 over 2 over 1/2, right? Minus, what's the tangent at 0? Think about being on the unit circle at 0. Isn't that the point 1 comma 0? So you have cosine and sine. So your tangent at 0 is going to be the sine, which is 0, over the cosine, which is 1. All right, so what is this? Square root of 3 over 2 times 2 over 1 minus 0. What does that give me? Square root of 3. Square root of 3. Part B. Part B. For part B, we have the integral from negative 1/2 to 1 of 1 over the square root of 1 minus x squared. All right, let's look at taking an antiderivative here. Now, let's run through that process again and how we do this in Calc 1, find the antiderivative. Ask yourself, is it a power of x other than negative 1? No. Okay, what do you do next? Can I think of what I take the derivative of to give me this? Some of y'all, yeah, some of y'all know, whatever. Then I tried what? A formula, right? And if a formula didn't work, I went on to u substitution, okay? Let's try a formula. That looks a lot like a formula to me. In fact, it looks like the inverse sine formula. So an antiderivative here is the inverse sine of x. And I want to run it from -1/2 to 1. So let's see, that's the inverse sine of 1 minus the inverse sine of -1/2. All right, what does this mean? This means the angle whose side is 1, and that angle has to fall between -pi/2 and pi/2. Give me the angle whose side is 1. Would it be pi/2 minus the inverse sine of -1/2? Where's the angle on the unit circle between -pi/2 and pi/2 whose sine value is 1/2? Wouldn't that be over here at -pi/6? Yeah. So this will be what? -pi/6, the inverse sine of -1/2. So I have pi/2 plus pi/6, or I could say 3pi/6 plus pi/6, and that gives me 4pi/6, but I could do better than that and call it what? 2pi/3. Not pretty, but it is the answer to what? That integration problem up there, okay? 2pi/3. Let's see what else we got. We're getting into some fun stuff here, huh? Well, I guess it depends on what your definition of fun is. Pretty much anything's fun right now, being locked down for COVID, huh? All right, let's see. This next example says, find the area under the curve. Find the area under the curve. F of x is equal to 1/x over the interval from 2 to 3 is the next example. All right, so what am I doing here? Looking at this graph, 1/x looks like that, right? Actually, it looks like that, and then it has another portion here. But I'm only looking between like 2 and 3 right here. And what am I looking for? I'm looking for the area between the curve and the x-axis and between 2 and 3. So I'm looking for that area right there. Well, we learned in the last section that the way we can find that area is we can say area is equal to the integral from 2 to 3 of my function like that. So really for this problem, I don't even need to draw this picture right here, okay? I could just integrate this. So let's see, let's take an antiderivative. What's the antiderivative of 1/x? Oh, that was a formula. Natural log of the absolute value of x, wasn't it? Let's run that from 2 to 3. From 2 to 3. So that gives us the natural log of the absolute value of 3 minus the natural log of the absolute value of 2, right? So that's equal to the natural log of, what's the absolute value of 3? Just 3. Minus, what's the natural log of the absolute value of 2? Well, the absolute value of 2 is just what? 2. Now, I can leave my answer like this for this class, that's fine. But I want to say Wiley plus, they're going to use the properties of logarithms. And they say if you have two natural logs being subtracted, you write as the natural log of the first argument over the second argument, like that. So natural log of 3 over 2. Now what I want to look at is absolute value. Let's go back to absolute value. We looked at some absolute value at the beginning of the semester when we were taking limits, okay? And what did we say at the beginning of the semester? We said the absolute value of x could be written as a piecewise defined function. It could be written as x if x is greater than or equal to 0, and it can be written as the opposite of x if x is less than 0, right? Remember, the absolute value of x is equal to exactly what's in this absolute value sign if x is positive or equal to 0. Absolute value of x is equal to the opposite of what's in the absolute value sign if x is negative, okay? All right, now that works for stuff like this as well. X minus 3 in absolute value signs, okay? We're going to say that's equal to what's in the absolute value sign as long as x is greater than or equal to some number, or it's going to equal to the opposite of what's in the absolute value sign as long as x is less than some number, okay? Now that number here was 0. The only reason that number here was 0 is because that's where the inside of this absolute value was equal to 0. Where's the inside of this absolute value equal to 0? Well, that's going to be when x is equal to 3, right? So the number we're going to put here and here is going to be 3. Now, don't just have blind faith in that. Check. What happens if x is equal to 3? Is the absolute value here equal to this part? If x is equal to 3. Let's test it. If x is 3, we have 3 minus 3, right? So that's the absolute value of 0, which is 0, right? Is that the same as substituting 3 in here? 3 minus 3 is what? 0. So that part works. Does this work for a number that's greater than 3? Like, let's say 4? Well, let's see. Let's test it. So what if we have 4 for x? We have the absolute value of 4 minus 3 when I plug it in there. Which is equal to the absolute value of 1, which is equal to 1. Now let's test to see if it's equal to the same thing here. What happens if we put in a 4 there? 4 minus 3 is 1. So that's equal. Now do the same thing here. Test it for values where it's less than 3 and see if that absolute value is equal to the actual function value here. Well, let's see. Let's suppose we pick a value that's less than 3. Let's say 2. Let's plug it in here. So we have 2 minus 3 in absolute values. So that's negative 1 in absolute values. So that's 1, right? What if I plug in 2 into here? Well, I get the same thing. Negative 2 minus 3. So that's negative 1. So that's 1, right? Again, it works. So I know that this is probably a good value, okay? Now let's try this. Let's rewrite the absolute value of x minus 8. Absolute value of x minus 8 in terms of a piecewise defined function. This would be a good time to pause the video, try it yourself, and then resume it, see if you got it right. Alright, so we know that the absolute value of x minus 8 is going to equal to x minus 8, or it's going to equal to the opposite of x minus 8. Now, where is that breakoff going to occur? It's going to occur where the inside is equal to 0. Where x minus 8 is equal to 0, so that means x is equal to 8. So this part's going to be valid when x is greater than or equal to 8, and this part is going to be valid for whenever x is less than 8. Boy, it sounds like somebody beating around in the rooms over here. I hope it's not picking up on a microphone. I don't know what they're doing. All right, why did I do all that? Well, I did all that because we have to integrate absolute values. Let's see. What if I'm told to find this? The integral from 0 to 10 of the absolute value of x minus 5. Let's suppose I want to integrate this. Well, I have no formula for integrating this absolute value that I learned, right? But I could break it up into a piecewise defined function. Then I know how to integrate that stuff. All right, how do I write x minus 5 as a piecewise defined function? I'm going to write it as either x minus 5 or the opposite of x minus 5, right? And this part is valid for whenever x is greater than or equal to 5. This part for whenever x is less than 5, right? So since I do not know how to integrate an absolute value function, what I'm going to do, instead of going from 0 to 10, I'm going to take the integral from 0 to 5, my breakoff point here, from 0 to 5, and I'm going to add that to the integral from 5 to 10. Remember we talked about that in the last section? We can break it up that way as long as we go through all these values, right? 0 to 10. I could break it up from 0 to 5 plus the integral from 5 to 10. Now, if I want to integrate this from 0 to 5, does that fall in the top section or the bottom section? The bottom one. Less than 5, right? From 0 to 5. So I'm going to use this piece of my function for the absolute value. So I'm going to integrate negative x minus 5 and put your dx. How about from 5 to 10? Isn't that like this portion right here? So instead of absolute value, I'm going to write in x minus 5. By the way, whenever we do this stuff, we don't have to be the ones to create it. Somebody extremely smart in math ended up creating a method for integrating this. And we just use it. We're just standing on the shoulders of giants, right? It's kind of like our cell phones. We know how to use it. We like using it. But if I told you to make a cell phone from scratch, good luck with that. But that's all right. Somebody can do that for us and we're able to use it. Same thing with this. All right, I'm going to factor this negative to the outside. You don't have to, but I like to. So I have the integral from 0 to 5 of x minus 5 dx. Plus this integral from 5 to 10 of x minus 5 dx. All right, so let's take some antiderivatives. So I have a negative here. And if I take an antiderivative, I have x squared